right, welcome back, everybody. Thank you. How's it going? What is new today? Huh? Yeah. There's a negative vibe I'm catching from class here. Thursday? Oh, good. Hello. I don't know that there's a way I can get comments. I don't know if they can comment on here. There's a live chat or something. I'll just see if I can type hello here. There, maybe they'll say hello back. I don't know. We'll see. Anyway, welcome back. It's good to see you. We're going to do this, right? Maybe, did I scare you away with CFA? Was that the problem? No. Yaya's back, so he's laughing, so that must not be the problem. Let's see. We left off talking about the CFA model, but then also we left off in the LaVon syntax. So let's go back to LaVon. But actually, let me just start off by framing it. Let's not start off with LaVon. Let's start with just talking about it. Do you remember the CFA model? Right? It was basically regression, but you just didn't observe your independent variable, right? And the example that we had previously, you know, this line, this part of the slide that you see here, y is equal to mu plus lambda times f plus error, that's for a single item. In our example, we had 6 items, so really what we're doing is 6 different regressions simultaneously. And that'll become more important when we get to path analysis, because path analysis is a bunch of regression analyses happening simultaneously. But we have to do factor analysis. We have to do this regression simultaneously, because without doing it simultaneously, there's no way we can estimate the factor indirectly. Right? Using a single regression term, regression line. If we only had one piece of data, this is unidentified. There's lots of factors that would work to give you that same result. Any questions on the CFA model? No. All right. Let's flip over to the website. I'm going to go back and close my R program here real quick. You don't need to hear all this. I updated my examples to include R script that has the graphics, the path diagrams that we talked about last time. So you'll see those in the script now too. So re-downloading things would probably be helpful. But here, if I grab this, go down through the code. Again, the LaVon syntax is right here. Remember, the way that we work with LaVon is that we, actually, let me just grab the code itself. Okay. Let's go with the real data, which is right here. So again, just to familiarize yourself with how things work in this class, we have this R markdown file, which if you grab the simulated version from the website, you'll get it to run. Right? But the way that we do this, to make it run, you have to hit the Run button and click Run All. And it starts doing work. And yes, evidently I did not download the package to plot things. So I have that one plot thing, and it's going to take an hour and a half to download all the auxiliary packages. It's like there's a plot package called semplot, S-E-M-plot. And of course, it makes you download like 15 different things, and maybe even more than 15 different things, because it's all the things, all the objects that it'll work with. So yeah, anyway, while we're looking at that, I am going to go grab the code again, and we're going to talk about it. That won't stop me from talking about code. So, going down into the example, my goodness. There we go. Here we go. Hey, quit moving around. There. Okay, let's hope this stays on the screen. Remember, the LaVon syntax works in curious ways, right? You have to create a very long character string that contains what LaVon's going to interpret as your model in it. And then you pass that character string to a function to run the analysis itself. Wow. should have done this before class. I've forgotten how long it takes. All right, going back to the website. So, while that's happening, this character string, once again, I have it in my syntax where it's model 01 syntax long. And LaVon, I'm giving you all the syntax here to run the analysis, but sure enough, there's shortcuts to it that you could take later on. And we're going to take those shortcuts, but I just want to show you all the parts of the model itself. So again, the first part is this line that starts with the word, pardon me, bless you. The hashtags in here, the pound symbols, whatever you want to see there, is are comments, just like an R code. So when it sees that in your code, it just goes, I don't read it. I'm not interpreting it. Then when you get to the line that says sit, when you see equal tilde, that indicates that the thing on the left-hand side of that is the latent variable. You can name it whatever you like. I think you can't start with a number, but you can name it whatever you like. We're just going to call this sit, because this is a situational forgiveness scale that we're trying to analyze. And sit, everything that shows up on the right-hand side has to be separated by plus signs. Those are all the observed variables that you think measure that factor, right? So factor is on the left of the equal tilde, and on the right are the observed. Now you'll note LaVon syntax is somewhat backward from our model in that we said y equals mu plus lambda f plus e, right? F is on the right side, y is on the left. But that's just because it's trying to look like M plus syntax, and I don't know why M plus syntax is doing that. This is the model, even though this syntax makes it look like the factor is equal to the sum of these items. It's not at all. That's just syntax. It's not equal to the sum of the items at all. Just note that that's just the convention they're using in syntax. Are we done yet? Yeah. Yeah.
It's almost the same as the LM regression when you predict without equal sign.
Right. In LM and regression, though, when you just have a tilde, but the dependent variable is on the left side. Here, the factor is the independent variable. Right. So just remember this. Don't let the syntax interpret the model for you. This is whomever started M plus, well, maintain started M plus syntax is backwards. It's not independent variable predicting dependent variable. You'd look at this, if you thought of a regression, you'd think, y is equal to a bunch of x's. That's not happening. That's not what's happening here. What you're specifying is 7 or 6 different y's, and each of those is equal to sit, the function of sit. So this is just their shorthand syntax notation for it, which is I dislike quite a bit, but what are you going to do? Everybody follow what I'm saying? Right? Just the key, because factor analysis, we don't sum up items to get our factor score. This is not what's happening. Questions? Other questions? Okay. So this next line, this is talking about each item itself with a single tilde, and the 1 represents the syntax to activate the intercept for each item. Now this is much more like what you would do in the LM syntax in R for the linear model, right? If you wanted to run just a linear model with just an intercept in it, you'd put dependent variable tilde 1, and it would work. Finally, when we get down to this next line, these are the residual or unique variances and covariances. Now remember that that's where we left off. What you see here is double tilde. The double tilde means what's showing up for that statement is a variance, right? So if this is our model, y equals mu plus lambda f plus e. Error is said to follow a normal distribution with a mean 0 and a variance sigma, or excuse me, psi squared. This is the unique variance, the notation of it. So what that is referring to, when you see sit1 tilde tilde sit1, that's referring to the variance that's attached to that error term. That talks about how much variance is unique to the item. So again, we put in 6 of these. And whenever you see the same variable on either side of the double tilde, it represents a variance. If we were to have a different variable on the other side, it would represent us as trying to estimate the covariance between a pair of items, or in this case, the residual covariance, what's left over after we predict them with the factor. How are we doing?
So for the first one,
Still installing. Yeah.
for the first one, it's the we are saying the situational forgiveness
Yes.
equal tilde.
Equal tilde.
The loading of indicator one
That's right.
plus the loading of.
Now, we're not saying that, but yes, that's what it's basically saying. Each of these is the loading for each of those
Which
variables.
means that all these indicators load in the first on this.
That's right, on that factor. Yeah.
And if we want to, because this is the loading, and if we want the variance for that indicator, we just square it.
No, don't say that. If you want the loading for it, we'll talk about it soon. It'll be estimated.
Okay.
Yeah, there's no easy formula there. The loading is going to be found for maximum likelihood, which means it's simultaneously the set of loadings that maximize a likelihood function. We'll talk about that a little bit. But there's no easy formula for loading. There's no closed form formula for it. If that makes sense. Finally, the last terms are for the factor itself, right? So sit was our name of the factor. It doesn't exist in our data set. All the other terms on the right-hand side here have to exist in our data set or it blows up, gives an error. Once you define sit in this set of syntax, once you define this word for the factor, you use it just like any other variable in the syntax overall, right? So that means sit double tilde sit means estimate its variance. Sit single tilde 0 means set its mean or set its intercept to 0. We'll talk about why we're doing that in just a moment. How's this working for all of you? Oh my goodness. This is the problem with that draw sim. They required all these packages rather than made them optional. So now it's installing all of them. If you ever read an R package, you can just say, no, it's optional that you install that rather than actually do it because, anyway, my fault for not putting it in first. Jeez, it's going to take a long time. Okay, once you have all of this put together, that shows up, remember, we named that quote, that character string model 1 syntax long right up here at the top. Right there. Can you read this? Do you want it bigger? You probably can see it on your own computer from downloading it, but let me just make it a little bit bigger. Is that better?
Yep.
Okay, so that's the name of the thing that contains all of the characters. It's the LaVon code. To get the model to run, we use this LaVon function. And technically speaking, this LaVon function is one that is the overly general function. If you use the LaVon function, you have to specify all the terms in the model. There's going to be a shortcut function we're going to use next, and we'll probably use it almost exclusively, called the SEM function, where you can omit a few things. You don't have to type as much. But we'll get to that shortly. I want it to compile. Go. Anyway, so this LaVon function, so what happens is we call this function, and we set the result equal to some other variable called model O1 estimates. And since you're familiar a little bit with R, you used R in which classes? Multivariate, was it? Right? In regression. Yeah, so in regression, you create your regression model, you'd have LM, and you'd set it equal to a variable. That variable is called an object. It contains all the information that goes into the analysis. And then you pass it to other functions to get the summary statement and so forth. We're going to do the same thing here. Model O1 estimates will contain all the information, the estimates, the data, the model specification, all of it for that syntax that you gave it right above. And the LaVon function takes several key arguments. The main ones are you have to give it the model syntax. That's what we created above. And then we say data equals HSF situations. That's the name of our data frame. Now you'll note in my R syntax code, a couple conventions. I like to label everything in the parentheses so that you know which goes where, which option it goes to. It's a good convention to be in, model equals and so forth, so each of the options that go with that. I also hate the assignment character. You know, in R you have to do. You know what I'm talking about? The arrow. There's a big. It's been a historical debate in R, but that thing right there does the same thing as equals. It just takes whatever's over on the right-hand side of it and makes a copy of it over on the left. That's what equals does. It takes less character strokes, less keyword commands. You can be like, well, there's a hotkey in RStudio for the assignment character. Yes, there is, but I have to press 2 buttons for it. If you think of how many times you have to hit assignment in R, that's like double all of your keystrokes for all those times. It's tough. So anyway, I use equals everywhere. You can use whatever you like, but this is how I work. The other syntax thing I do is I use this, I think it's called camel case, where you capitalize words that are distinct in the syntax as well. So I'm going to try to be consistent with that as I go. Not done yet. Going on 10, 15 minutes. The estimates, so we have the key ones that it wants are the model syntax and the data, right? So model is where the syntax goes, data is where the data frame goes. The next options right here are what we're going to use. The next two are what we use in this class. Estimator equals MLR. That is to use robust maximum likelihood to estimate our model. That's going to be almost exclusive when we do a CFA. We'll do that. And we'll talk about why in a few, well, several lectures from now. Mimic equals M plus is the other option that we use. And we use that because, well, if I'm going to be literal, the homework system that we have online was built with M plus. And it gives pretty much the same answers as M plus in that way. But if you don't do it that way, it's not guaranteed to exactly give you M plus answers, but they're still pretty close. So just to do this, a lot of people in this, like the social sciences love M plus, but I've decided I hate it. So. I don't say I hate it. It's fairly okay for what it does. It costs a lot and breaks too much for my own liking. Plus, they're very secretive about what it does. Whereas, so I'm much more in. I've recently come into loving open science, and R is part of that. You can go into the LaVon function and see how it's estimating things. And if you know anything about it, then you can evaluate it. Whereas if someone says, well, yeah, mine just does SEM, you don't, what exactly is it doing? Now, M plus does have some technical dependencies that in the last time I checked, haven't been updated in many, many, many years, but, you know, that's how it goes. So I got it to work, but yes, I found this also. I have to redo this again, all that running of the code. Let's try this one more time. There we go. Okay, so now I think I can run it all. So let me just show you. I was stalling for time there a little bit to try to get to the part where I can show you how the input and output works and show the object to you. So now it's running everything. So again, this is what you do with the markdown file. You bring it down from the internet, you press play, hit the run button, and then if you want to see the document in markdown form, you hit the preview button and it shows up in the viewer pane if you've selected output to previewer pane over here. But for us, what I want to show though is get down to LaVon syntax. Here we go. I want to show you this right here. This section of code, Model 01 estimates. If there was something wrong with the syntax, it would give you an error and would not return an object to it. Just say, hey, model's broken. When you do run that, if you take a look over at the environment, and remember in RStudio, the environment talks about all these, all your variables, and Model 01 estimates is there, and it says formal class LaVon. That's a type of object in the R system. It's an S4 object that contains stuff. You don't need to know that. What you need to know is how do I get my numbers out of it? And that's with the summary function, right down here. So you get your result, it works, hooray, everybody's happy. You know, I wish it would play like a, you remember the Windows exclamation point sound? Dun, dun. I wish it would play that when it runs successfully. Like, dun, dun. That would be great. But no, Model 01 estimates is right here. Actually, it'd be terrible if it goes after it fails, because if you're learning this for the first time, there's going to be a lot of Anyway, you run this part. The summary statement allows you to put Model 01 estimates in. And there's some other options that are only there for the LaVon objects, and I'll talk about those here. fit measures is how we determine whether or not the CFA model fits. I run it pretty much exclusively with these in unless I'm trying to shorten my output to show you. R squared tells you how much variance the factor accounts for on the item itself, right? So it's like your R squared that you would have in a regression, because each of these items are regressions. And then standardized talks about estimates that come from, when we talked about removing their units before, those are the standardized estimates. They will output those as well. So this is all, put them in a nice summary form, and that summary looks like what you see right here. Looks like M plus, exactly. It's trying to rip off M plus. Although I don't know, is it ripping off if it's an open source free package? I don't know. What do you think about that? No. Speaking of this, just intellectual property wise, the university, they're very concerned about intellectual property. So if you write software, first of all, my teaching is they technically consider it my intellectual property, so I can do whatever I want. They like put it on YouTube. They don't touch it. There's probably because there's not much money to be made in it. But then for the software, right? If you write a piece of software, they're a little bit more interested, right? If you think your software could make $10,000 or more, you're supposed to file a claim with them, and then they're going to they own the software, right? So they own everything, every part to it. But what I've heard through the university channels, that licensure that they talk about through the KU office of, what is it? KU intellectual. I've forgotten what it is now. Anyway, through the research office, they have an intellectual property wing. They're less keen on trying to sell software because someone's going to come along that has a lot more resources than KU and basically develop the thing to do the same thing that's not copyrighted, that's not yours. Right, so if you're like, I'm estimating an SEM model, there's nothing to stop Microsoft from building that into Excel or something like that, right? That's really successful. They're more interested in, like, if we're in biology and we come up with a new way of splicing genes, or we're in pharmacy and we come up with a new vaccine, they'd really want to get their hands on that. It's harder to replicate elsewhere. So yeah, the software world, if you're the one writing the software, it really feels very frustrating, and I've heard reports that Bank Butane is very unhappy with this. I don't blame them for being unhappy, but this is just the way, unfortunately, software works. So, anyway, blah, blah, blah. Long story short. The first part of the output that you see here is model fit information, which we'll cover shortly. All that. The next part gets into parameter estimates. These are the factor loadings right here. And then in the parameter estimates, you see several columns of the output. There's one for estimate, one for standard error. The z value, does anyone want to take a guess as where z comes from? This is called a Wald test, by the way. No? No? It's a z, it's not chi-square. Z would, the hint there is z is usually what we reserve in statistics for standard normal, like a z-score. Anyone heard Wald test in multivariate? I'm testing Billy now. Well, I'm testing you. I know Michael has. A Wald test is a test where we take the parameter estimate, divide it by its standard error. And this gives us a test statistic that is, in theory, as n goes to infinity, it converges in probability to a normal distribution. That means we can test that parameter from being different from 0 using this z statistic right here. So that's what a Wald test is. 17.906 tells us that this value, this is the p-value, the probability of finding a z greater than, an absolute value of z greater than that. That's essentially your two-tailed test off of a normal distribution. Right, you can go and find it using the p-norm function in R here, right? The probability that comes from the normal curve, although this is infinitesimally small with a z value of 17, right? So that's what a Wald test does. The cool thing about Wald tests in maximum likelihood is that Wald tests converge with, have you heard of a likelihood ratio test? Okay. Likelihood ratio tests, if you were to take this model and let's say if you wanted to go and see if this value is actually 0, you could estimate the model where you've estimated 1.234, and you can compare it with a model where you fixed it at 0. Not drop the variable, but fixed it to 0. The likelihood ratio test will tell you essentially the test of that same hypothesis, right? One model is nested within the other. Right? the results of the two as n goes to infinity should be asymptotically the same. In the likelihood ratio, you have to fit the null model and the alternative, and the null has to be nested within the alternative. In the Wald test, you fit the alternative model. And there's another test called the score test where you only fit the null model. Like you don't even have the variable in it, and you can test to see whether you should have added it. And we're actually going to use that later on in SEM as we come forward. Something called modification indices, they call it, but they're score tests. All three of those types of tests are asymptotically asymptotically equivalent, meaning they should, the bigger your sample size, the more they should converge to the same number. Okay. So those are your factor loadings. Let me just double check where I'm at with my slides. And the unstandardized solution, the thing at the top, talks about each of these in sort of the raw metric of the variable itself. So factor loading that you see right there, let's take a look at sit1r. This does anyone want to describe, it's a regression slope. Does anyone want to interpret it for me while I take a drink? I'll do this first one. It's a factor. I can understand being different, but it works just the same as regression. It says for every 1 unit increase in the factor, in this case f, or what we're calling sit, the variable, sit1r, goes up by 1.234 points. Mayumi.
Wait, I don't know if I'm looking at the same thing as yours because I'm so sorry. Going back to estimate and standard error and z-value.
Yeah.
My z-value says 21.9.
You might. Are you looking at you're looking at the simulated. I'm looking at the raw.
Oh.
But I can switch. Let me just switch to simulated so you can all see the same thing. That would be a good idea. Give me a.
That's why I didn't match the number. Oh, okay.
Yeah, let me just. But you make a good point. I'd rather just have the same number in front of you. But I wanted to give you something to play with data. So simulated was supposed to do that. But let me just do that real quick. What should happen is I don't have to reinstall all of that stuff, right? So this should go a little bit quicker. You can see all the objects being populated. Go, 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 go. I didn't have to run the whole thing. I could run each individual code block separately, but some blocks depend on others, and so just running the whole thing makes it easier. And, all right, Miami, let's see if I got this right. 21.977? All right. That's the way it's supposed to work. Let's see how many times I can actually make it correspond to what you have. So, interpreting this coefficient, the unstandardized estimate is just what we call estimate here. And it's unstandardized because the way you describe it is units of, this is the increase in the units of the variable. So this sit1 goes up 1.317 units per 1 unit increase in sit. So what is a unit? Well, we usually describe them as standard deviations, right? Sort of. Actually, no, these are actually raw units. The raw score of sit1r goes up 1.37 whatevers. In this case, Likert points. 1 1/3 categories higher someone rates for every 1 unit more of the factor they have.
And the factor itself is on what scale?
That's the next question we have. The factor, the way we set this model up to estimate, we allowed it to be a factor with a variance of 1. We fixed the variance of 1. That's one thing we have to set in our analysis. We have to set the variance of the factor, or the estimation method for it. We have to set the mean of the factor. The mean of the factor is under the intercepts column as a 0. Right? So what that means is for every 1 unit of the factor, you're saying I'm going up 1 standard deviation. If the variance of the factor was 10, 1 unit would only be 1/10 of a standard deviation. So in theory, it wouldn't be very big. Right? So what you would expect with a not very big increase in that number is that this estimate value actually the decimal would slide over one place and it would be 0.1317. Right, which looks really small, but again, it depends on the variance of the factor to describe its units. Yes?
Actually, I'm confused a little bit about like fixing the factor to 1, the variance of the factor. Shouldn't be like the estimate, like the raw estimate should be like the upper bound should be 1 because we fixed the factor to be 1.
No, no. In this case, it's not 1 because we didn't fix anything about the variable. So the variable itself has its own scale and its own estimate of variability. Right? What's left over for this variable, this is the unique variance, is 1.475. But if we go up higher, it's a really good question, Yaya. Thank you for asking it. What you'll see is the variance of this item is 3.209. Right? So that's the units that the variable is on. If we had standardized it so it has a variance of 1, then yes, the factor loading has to be between -1 and 1, like a correlation in that regard.
Also, there's a way to identify the model as marker variable.
We're getting there, yes. We'll have other ways, but for right now, let's just want to concentrate on the standardized factor to express what each of these things mean, and then what the standardized versions mean. But we'll get to different identification soon. Questions? Okay, so once again, everything in the estimate column is the unstandardized, and this is highly susceptible to the variance of the item, and depending on how you've estimated, the variance of the factor. Right? So if I run this analysis this way with the standardized factor, and there's other ways of doing we just, as Jihan was saying, we don't have to do a standardized factor. We could do something where we essentially estimate the factor variance. If he runs it that way, our numbers will change in this column, and that's because the scale of the factor has changed. Right? That doesn't mean the model is any different. Actually, the model fits the same, but the difference is because the latent variable doesn't exist, we have to specify the scale it's on. Right?
So
go ahead. Here, let me show you real quick. I can go up to my LaVon syntax, and if I set the factor variance to 10, right? Actually, let's do this. Factor variance to 100, because the standard deviation of 100 is 10, right? The square root of 100 is 10. Let's see what happens. Right, so I can go change that. You can do this in your code too. We can hit play. That reads that puts the character string into the model 01 syntax variable here. And if we drop this part of the output, this STD.LV, we make that, actually, if we just change that to false, we can drop it. Its default is false, but just change that to false. What we get is it ran. And now let's take a look at the estimates. You'll see the numbers at the top. I don't know if you just saw before, but my numbers at the top are the same. All the model fit is the same. That means this model is identical. I've just decided to set my factor variance to 100 rather than 1. Why would you do that? Because your advisor wants you to. You know how they work. Or actually, it's not your advisor. It's that outside member of your committee. You know, you put them on there because they're part of the graduate school, and next thing you know, they're telling you what to do that doesn't make any sense, right? Anyone have that experience on your committee? No? Maybe? Okay. Not that they're willing to say. That's right, we are being recorded here. But take a look what happened though, right? You see the estimates now? Instead of having 1.3 whatever, it's now 0.132. We moved the decimal place over, and that's because we made the scale of the factor 10 times bigger, right? 1 unit of the factor is now 1/10 of a standard deviation, whereas 1 unit before was 1 whole standard deviation. Yes.
Can you scroll down?
Yes.
Okay.
There we go. Variance right here, 100. There we go. All right. So that's basically it. And also on that note, the way you can tell which parameters were set or fixed in an analysis, they will not have a standard error, and because they won't have a standard error, there's no z-value or p-value. Right? So when you see sit, and you see it under the variance, that means the variance of this variable with no standard error, that means it's been fixed. You fixed it to that. How are we doing? So again, the unstandardized estimates are subject to debate, and that's because, I don't know about debate, it's subject to difference, because it all depends on which way you set your scale of your latent variable. Right? So that may sound problematic, but it's not. Because there's another solution called standardized. And this is M+ language over here. In LaVon, what we really are looking for is the following. STD.all is what's called in LaVon. So let's talk a little bit about this. In unstandardized, it's true that the variance of the variable is equal to the loading squared, and that's what we're talking about, times the factor variance plus the variance of E. Right? So you know what you're getting back here is the variance of Y. Right? And you can go, and we saw the variance of Y was a little over 3. We can do the math. You can show how that works. It all fits in together. But to standardize this, remember the lambda, this lambda term, it's units of Y per units of factor. And remember the standardization process, we have to remove those units. Right? So it's like saying we're going to multiply that by the standard deviation of the factor, removing the units of the factor. And we're going to divide it by the standard deviation of the variable, remove the units of Y. Right? So basically the transform solution is what you would get if you allowed the factor to be 1, variance of 1, and went and made a z-score out of your item so that it had a variance of 1, standard deviation. So let's take a look at what that appears. Now, this is the std.all column. I'll tell you a little bit about the std.lv in just a moment. Let's do std.all. Remember, that takes, again, if lambda, the unstandardized lambda is units of Y per unit of F, what it's basically doing is multiplying this by standard deviation of F, which cancels the units there, and the standard deviation of Y, which cancels our units. Right? But let's see what happens. Have you run this on your computers? Anybody? Miami, you ran this on your computer, right? Do you have the version that doesn't have the 100 factor variance on your computer right now? Okay. Here, let's do this. The standardized loading, 0.735. Remember that number, 0.735. Right? It will be identical. If we change the unit so that we made this instead of 100, we just made it 1. We hit run. We hit run. And we hit run. What you'll see is we're back to 1.317 over here for the estimate. But the standardized estimate is 0.735. So when we do a lot of reporting for the factor analysis results, so we use the standardized estimates. And in fact, we use this fully standardized, standard std.all more often than not. Because that tells a scale that is, that tells us numbers that, you know, regardless of how you identify the model, those are the numbers that will be the same regardless of you use one, factor variance of 1, factor variance of 100, or some other number. Right? Is that cool? Sort of. So what does std.lv mean? That is where we take the units, we divide by, where we multiply by the units of the factor. But we do not standardize based on the item, the variable. Right? So what that does is we multiply by the standard deviation of the factor. Well, the standard deviation of the factor is value of 1 in this one. If we were to go back to our 100 example, right here, run the code, we get, take a look at what happens. 1.317 over here, because this value gets multiplied by the square root of 100, or 10. So what this column std.lv tells you is what the analysis would look like had you used the standardized factor version of identification. Had you gone into the analysis and said in that LaVon part of the syntax, had you either put a 1 times the factor in the syntax, or had you put std.lv equals true, that's what that column tells you right there. So why is that important? It's not. I mean, each of these results is the same number, effectively trying to tell you the story of the same thing. But a lot of times in SEM, we're going to want to run an analysis where we predict the factor, right? We're going to have in a variable, like we may have 7 regressions with y, but then we're going to have f is equal to some other variable, right? Beta 0 plus beta 1 x plus e. Well, this f right here, if you want to try to say, like, maybe you have a mean difference in factors for men and women, right? So x would be a 0, 1 variable, right? Then e is the residual variance, and once you predict it, it should shrink, right? Well, if you go and fix your standardized factor, you're fixing the variance to 1, the program won't allow this to shrink. It'll be set to 1. All the other numbers go crazy. So in SEM, there's a real big push to have an estimate for the variance, because it'll help you describe a little bit easier what's happening when you're saying there's a mean difference. Let's say there's a mean difference between men and women, you'll have an R-square that is easy to calculate. So, but again, all these models are synonymous, right? Whether you put 100 for the variance or whether you put 1, they're equal. It's just you have to set the scale, but it has ramifications for what these parameters have to be. std.lv is a very common method of setting the scale. In fact, have any of you have taken Billy's IRT class? No. He's teaching it this afternoon. No. I think it's this afternoon. Maybe Bayesian is this afternoon.
No, this afternoon.
That's right, this afternoon. Almost exclusively in IRT, we have a STD, or we use a standardized factor version. And the reason for that is when it shows up, when you're trying to give somebody a score, like if your whole purpose is not this, right, but you're looking to say, hey, here's your score, Craig, then it's just sort of an easy way to get started. All right, the uniform, we set a z-score metric. We sort of know, we assume the factor is normally distributed. We sort of know the proportion of people above or below. We have a nice common reference. So if you're only knowing this method to provide people better test scores, you probably only want to have the standardized latent variable. If you're not, if you're trying to do it for other analyses, you probably don't want it standardized. It's a common paradigm. How am I doing? Have I lost you? No. Good. So we're talking all about the model parameters. We haven't yet talked about factors themselves, the scores. We're going to get to those eventually. But right now, we're just talking about model parameters that go into it and how it fits. So that's those are the factor loadings. And here, I'm going to go back to my analysis and just turn this to true, just to be like we were before. Bless you. And make this 1. Although it's sort of superfluous, it's too much. I can just fix the standard std.lv to true, and it should have worked. But I'm just doing this for completeness sake. Going back to our original model here. So this is a standardized factor that we're using to estimate with. These are the loadings, right? The other part of the loadings that I want to mention is, if you look at the loadings, which one do you think the factor has the biggest relationship with? 1.317, right? But that's not true. Because this is the units of y. It's relevant to the scale. What you're picking up on this one is this first variable might have more variability than the rest, right? Or might have less variability than the rest, actually. So it would look like a bigger increase. The way you tell which one is really the stronger is std.all, because this is assuming each of the variables have the same amount of variance. So looking at this right here is called comparing apples to oranges, essentially. Colloquialism. Whereas this is trying to provide a standardized metric, and the third one looks like it's the best.
I'm sorry, I'm a little bit unclear about the idea. Okay, so now we have the unstandardized raw data for the estimates itself, factor loading, and you talked just a minute ago about the standardized.
That's right.
No, not standardized.
This one.
Yes, one.
This is standardized based on only the latent variable, not the item itself. So it's only partially standardized, right? So we're basically saying, what if we had a variance of 1 for the latent variable? What would these look like? Well, these are identical now because we actually do have a variance of 1 for the latent variable. It's interesting. Yeah, it's funny because again it's somewhat arbitrary, but it has to be because the variable doesn't exist. So if it doesn't exist, we've got to put a scale out there to anchor it to. And there are certain rationales for using different types of scales.
Is it always that the raw estimation will be equal the standardized latent value?
This and this?
Yes.
If you make your is only equal when this is equal to 1. When you set it to 1. Like if we go back here, let me just set it to 100 real quick.
Yes.
Ooh.
You set it to 100.
It will be different. And you know I didn't run that top part of the code. All right, it'll be different, but you understand where I'm coming. I didn't run the top part yet. So this will still be 1.317, but this was 1 decimal over.
Based on this case, you
It's warm in here, am I right?
Yes.
Okay, it's either freezing or warm. We open the windows, it doesn't actually help. I need to call the assistant dean, Lon, and he'll get up here and fix it. We'll try to get it fixed. I'm supposed to do that as part of my new role. It's me. All right. Anyway, associate chair. Yeah. Question.
I have a question about the language.
Mhm.
So you said that the best way to tell which factor loading is the best.
Yeah. Or better yet, it's which item is most related to the factor.
Which item is most related?
It's actually what this is representing. This standardized loading is like a correlation of item with the factor itself.
Which item is
Most related. That's right. What's that?
That's easier.
Yeah, it's a correlation of the item with the factor.
most related to the factor.
That's right.
So this is mainly what we did for.
That's exactly it. The predominant thing that you see in a lot of articles is the standardized solution. Now, you may not see that in some, and that's fine, because if they gave you the variances of the items, or better yet, if they gave you the factor variance, you by hand can compute what this happens to be, right? Because we know what the variance of the item is. The variance of the item is this squared plus this. And we know what the variance of the factor is. So we have the standard deviation of the factor, we have the standard deviation, and we could go and create the standardized effect if we wanted to. So those are loadings, and that's where the magic happens. Yeah.
How come they typically don't report that?
Shada.
Yeah. How come they don't report that?
The
All.
well, that's usually what is reported.
Okay.
There may be cases that you see articles where they're not, and those are the people who are probably really well versed in SEM. But again, if they report the complete set of output, you can get back to it. Yes. Other questions?
Would you say that more often than not you see that in older articles that the all isn't reported?
Maybe. I don't know. The articles I read don't even have they're just they don't have a lot of numbers in them. But yeah, no, that makes maybe that's the case.
Would we call this? Can we make like a loadings matrix out of these and report it that way?
Yeah, absolutely. One of the ways that people do it is just put a little vector of the loadings and
Similar to your least favorite EFA, you might have like a pattern matrix.
Yeah, that's right. That's right. Don't get me all angry now. I'm trying to feel the tension come up. I need to take it. Sit down. I got an email from a professor today talking about EFA, and my reply was, these statistics are from the you shouldn't be using statistics or methods from the 1930s. There's better tools. So anyway. Yeah. It's ironic that I got this email, but I digress.
So you would look at these before you would even look at like model fit?
No, And actually, that's the thing.
Okay.
When you're looking at these numbers, they're all dependent on model fit,
Yeah.
right? So we haven't gotten there yet. This is a really, really good observation. Model fit means everything. And the reason for that we're going to get to, but effectively, if your model fits, it means what these numbers are trying to do is replicate the pattern of variances and covariances in the data. And if the model isn't fit, it means you're missing, or better yet, these numbers are getting stretched and pulled to try to represent numbers that don't really work. So they'll be biased. So the only way that you can really take these numbers at face value is to ensure that the model fits the data, and we haven't talked about that yet. This is more just trying to familiarize yourself with the model.
So this is for like individual scales, then we go to the whole model.
That's right. Now, speaking of exploratory factor analysis, you'll note the standardized effects. They range between 0 and 1, which is what you'd see in an EFA. But if you wanted to know whether the item actually loads onto the factor itself, you don't look at the actual raw value of that. You look at the p-value, right? Because that p-value tells you whether or not lambda is significantly different from 0. If p-value is really small, there's a really good chance this is significantly different from 0, and therefore the item loads onto the factor.
Can you repeat that again?
Yeah, if the p-value is really small, this p-value is for a hypothesis test comparing the factor loading to 0. So if the p-value is really small, you reject that null hypothesis. And your assumption then is that it's not 0, which means the item does measure the factor.
So what's the algorithm the common algorithm for to indicate that this is significant? Because
the common alpha level. People always use 0.05. It's actually the way it works out. Yes, if you use 0.05, you have lots of significance tests, and you have an overall inflated effect and whatever else. But the way it works out in practice is these are almost always really tiny values, right? So it's really, really rare to find anything that's off of 0. And that's because these items are what's defining the factor. So it's doing everything it can to get a loading to make it work effectively. It's anecdotal, but you can use whatever you like. If you want 0.001, that's a good stringent estimate. If you use that, you'll pretty much come up with the same results as we see most of the time.
So 001 or 01?
05 is what I see people use. 0.05, the typical 0.05, and then people are less worried about type 1 error because you have multiple tests, although you should be, but yes. Okay, I like your questions. This is good. Let's look at the other parts of the output, the other parts of the model, the intercepts. Let's take a look here. That is mu for this factor model, right? And we talked about it last time, but that actually, when the factor mean is set to 0, this is going to be the mean of the item. And if you want to see up in the output, a little bit higher, we see the means. The first item is 4.443, the second is 5.287. The first intercept is 4.443, the second is 5.287. So oftentimes we ignore the intercept altogether. Don't care, don't want it. It's important because it sort of tells us what people are in the, we need it in the model, but we don't do a lot of inference on it. Just like in a regression model, you don't do a lot of inference on the intercept, right? But similarly, all the columns of the output remain the same, right? This p-value is for a test of hypothesis of whether or not the mean is equal to 0. Does anyone care that the item mean is 0? Well, let me give you a hint. This is a Likert scale with 7 options, and the lowest number someone can put on an option is 1. So the lowest the mean could conceivably be is 1. So therefore, no, who cares? It doesn't. We don't care if it's 0. It's sort of a nonsense test, right? The standardized coefficients are also somewhat nonsense. What is the mean divided by the variance of the item times the variance of the factor? It means what would happen, what the mean of a z-scored item would look like, or not even a z. It couldn't be a z-scored. It's a standardized, but only by the variance, where you didn't subtract off the mean. If you just want to see that, it doesn't make any sense. It's hard to even describe. And finally, the variances here. These variances represent the amount of variation left over in the item that's not accounted for by the factor. So in a regression model, we're worried about R squared, which actually shows up down below it. This is essentially what we call measurement error. Right? This is how much measurement error is left. That's how much variation in the item responses that we didn't see because of the factor variation. Unique variance, that's right. Sometimes called residual variance, sometimes called error variance. You'll again see there is a standardized estimate here. Now this standardized estimate does get reported. Right? It's sort of but it happens to be 1 minus R squared.
So, like the R squared plus standardized would give us the standardized.
Yeah, what happens is if you wanted to go with this, R squared comes from here. That formula that we see here, the variance of y is lambda squared plus the variance of factor plus variance of error. Well, if we standardize our output, variance of y is 1, right? So this has to be proportion due to factor, and this has to be proportion due to error. Right? Now, I will note, this is for an item that measures one factor. If you have multiple items, then we have to do something with the other lambdas as well. But worry about that later on. You'll still get an R square out of it. It still will be 1 minus the squared standardized unique variance. But here you see the R square for each of the items. That's right. R squared is essentially another reporting of the standardized output. So again, just like we saw with the standardized loadings, item 3 seems to have the factor account for most of the variance. Right? It's R squared is 0.633. The other ones are in different values. By the way, these R squareds look really big if you're used to looking at R squares in regression for studies in social sciences. Right? R squares in regression are like what? Usually 0.1, 0.15, something that's usually pretty tiny. And that's because we're creating a latent variable out of these items. It's going to be really related to them. Right? We didn't actually explain the variation with something we've observed. We're sort of just saying, if it's the case that this thing exists, then this is what we would expect for an R square itself. But because we're defining it as part of the analysis, it's somewhat tautological. It's not like saying an X said, we found an R square of 0.63 when we predicted a thing with X, or something observed.
Can you please go up like to the indicator loading? No, indicator loading.
Right there. Yes. Question? Yeah.
No, I'm thinking about because the variance is R squared and the.
Yeah, here, if you want to see it, it's 0.735 squared. Plus 0.540 should give us right about 1, although it's not. It's a little over. Oh no, it's not 0.540. It's 0.460. There we go. That's our total variance for standardized. Okay. Going back to the lecture slides. All this, by the way, is written in the lecture slides, what I just said, but also is written in this example text that you'll see. And I'll get to your question in just a moment. The preview of the document, and this is actually one of the things I'll ask you to read. Read this, right? Because it describes everything I'm saying in hopefully better detail than what you're getting in class here. But there's lots of text, and you'll see below it we have each of the terms split up with a description around it, right? Yes.
So I remember in the lecture slides it says like CFA is for continuous data. So for this case, this question, I feel like the answers they're not really continuous.
Right. I agree.
Does it matter?
Yeah.
If we use it in here?
It does matter, but it's used very, very commonly. So I'm showing you sort of what gets done. But in the next section of the course, when we go to categorical analyses, you'll see how to do it better. But yeah, it does matter. The results that you have here aren't guaranteed to match on to the results that you do with the categorical version of the analysis. And that version of the analysis is likely much more accurate. the flip of that is it's a lot harder to make that version of the analysis work. Like it's really difficult sometimes to get that to work, but I'll show you ways to shortcut it. Other questions or thoughts? So do you feel like you have a grasp of what the model is looking at now? One thing I also have down here, because you saw it, it took us 15 minutes to install it, so we got to show it now. Right here, it's really easy to plot the path diagram. Although the numbers themselves don't look great because they color code by the size of the load, the estimate itself. And so when you put the mean structure in, remember here's the triangle. Although there's not one triangle, it's like a triangle per item. It does that, but you see this is one factor for it. You can change the estimates to be, let's see here. There should be, I think there's an option for mean structure, but I'm not finding it now. No, but you can also, this is the actual raw estimates, but there I will find it and talk about it later, but basically this is what you can just pass your LaVon output to, and it will draw a path diagram for you. And it'll take some tweaking of each path diagram. It's a pretty uninteresting function, so it may take some tweaking of the options to make it look like something you want to show, but this does do it for you. It does it pretty quick. So. All right, how's everybody feeling about this? Okay, so what we just did is a series of regressions. In fact, we had 6 of them. Now, this example that you see on this slide is if we had 2 factors, right? But if we did have 2 factors, basically this would look like this. If we say the first 3 items load onto the first factor, each one gets a factor loading for the first factor, but it gets a 0 for the second. And they don't show up. Similarly, if the last 3 items loaded on the second factor, they get a factor loading for multiplying the factor for those items, with a 0 for the first, and they don't show up. And so what you end up getting, you have this overall matrix version of it. If you read a lot of the SEM literature, you start seeing matrices all the time, but I don't want to get into that right now. But that's basically how it happens, that where you say how many factors you have and which items load onto each factor. What makes this confirmatory is if you don't believe an item loads on a factor, you put a 0 there. If you come from the EFA framework, you're probably thinking, is that okay? The answer is yes, because ultimately, if the model doesn't fit, you're going to reject it anyway. Right? So you're going to say, I have 2 factors. They load like this. You look at the model fit statistics, you're going to be like, no, that's not 2 factors. There's something else going on. So yes, it is okay. In this case, because you are allowing yourself to be wrong. Let's just put it that way. So here are what the role of each of these parameters do. As we noted before, the item intercepts, right, were equal to the item means whenever we have a factor variance of 0. That's because the item intercepts effectively are the factor means. The slides say predict the item means. But basically, when you form a model, I mentioned before, the patterns of means, variances, and covariances sort of describe what the model should look like. The intercepts go to the mean side of it. The item error variances go to the variances of each item. And you'll note we actually recover those perfectly as well. And finally, the factor loadings predict or recover or imply the covariance between the items. Right? So there is room for a misfit from the factor loadings. In a typical CFA like we just ran, all the means fit perfectly, all the variances fit perfectly, but the covariance may not. And that's where we have to go and focus our efforts on determining model fit. So how does this work? Here's the formula for it. Right? If, I have the equal tilde reversed here, sorry about that. If F1 was measured by items 1 to 3 and F2 was measured by items 4 through 6, we would see that the unstandardized covariance of items Y1 and Y3, now they're measured by the same factor, would be predicted by the loading of the first variable times the variance of the factor times the loading of the second variable. That's our prediction for that variance, that covariance. That may not be accurate, but that's where model misfit's going to come in.
Can you repeat that again?
Absolutely. If our model is accurate, the covariance of a pair of items, like in this case y1 and y3, measuring the same factor, is the loading of the first times the variance of the factor times the loading of the second.
Okay, when you say if the model is accurate,
Mhm.
and there is a
Oh yeah.
predictive range here, like
Right. This is exactly why
and this fits, so
this is exactly why it works this way, is because CFA is going to say this is the structure we're expecting to find right here. Right? If you say there's two factors, then I'm going to go and look, and this variance of y1 and y3, I don't know what the loadings are, but I'm going to estimate them such that this is true. Right? And that not all the time, that doesn't fit the data all the time. In fact, most of the time it doesn't. Right? And so because it can be different from the data, that's where you can say, no, this can't be two factors. Because if it were two factors, I'd see that this is a good prediction. It's not. So that's where we get our chance to test. That's where model fit really comes from. And
so the misfit might be attributed to the idea that one or more of the indicators might be related to the other factor.
it could be, or it could be a factor that's not even on the instrument altogether.
So what about like the related errors between the?
We'll get there. Hold on to that question right now. Let's just focus on. We don't have any related errors yet, right? But we'll get there. No, it's okay. We'll get there. If we add that, well,
Okay.
we direct here. I'll just say it. If we say that y1 and y3, there's an additional, their errors are correlated together. That actually becomes a model parameter that adds to this. And when we say they're correlated, then we perfectly predict the covariance, which is sort of cheating. The other reason why it's cheating is if you're saying this is a factor analysis, and I'm making an argument that these set of items measures factor 1. If you have to put a unique or a correlated, an extra term to it, saying that these items have extra covariance that the factor isn't explaining, that means factor 1 isn't truly factor 1. It's factor 1 and something else. So I like to call it factor 1 and stuff, or sort of factor 1, right? Because if it's true, if you think about the measurement principle, what we're talking about here, if truly it is the case that factor 1 is measured by these three, then this covariance should be accurate, right? And if it's accurate, then even if you put an extra term to it to say there's a residual covariance between these items, that would be estimated at 0. It wouldn't be needed. Right? But if it's there, it's saying, yeah, the factor 1 sort of explains some of the covariation, but not all of it. So I just put this in there, and yeah, the model fits now, but still not. It's not factor 1 by itself. Does that make sense?
Yes.
So covariance is with the unstandardized effects loadings. You take the standardized loadings from std.all, right? Then we know the variance of the factor is 1 because that was part of the standardization process. And then the standardized loadings get multiplied, but what that's implying is the correlation. Right? And that's because correlation is the standardized version of covariance, right? You take covariance, it's in the units of y and the units of x. And you divide it by the standard deviation of y times the standard deviation of x. You cancel the units, you get correlation. So that's what's up with that. Okay. The other part of this I wanted to say is the interesting thing that you get here. You remember introductory stat class way back when, where they said a correlation between a variable x and y implies one of three things: that x causes y, that y causes x, or that there's some other thing that you didn't observe that causes both of them. Yeah, sort of, almost a mediator, but not quite. Yeah, it could be a mediator. I guess you could call it mediator. F is the mediator. F is the thing that causes them. The factor is now the thing that causes the correlation. So that's what this is trying to do. It's saying that's the other variable out there. That's the reason why they're covariant together. So if you knew F, you describe all the relationship with it between the items that you have. How are we doing? All right, 5 minutes. I'm going to keep going if that's cool. Till 5 minutes. I hate keeping you longer. I'm sorry about the last time. So that's items from the same factor. Items from a different factor, what shows up in the middle is a little bit different. It's the item, the loading for the first item times the covariance between the factors times the loading for the second item. Right? If you want to know where I'm getting this from, there's something we call a tracing rule, which is a little bit weird. If you want the covariance between y1 and y3, you trace the paths and multiply everything in between. Right? So you got lambda 1, variance of factor 1, lambda 2. You want the variance of y1 and y4, trace the paths. Lambda 1, covariance, lambda 2. Right? So if you think of it, it's an odd way of calling it, but it's a tracing rule. Really where those numbers are coming from. I don't know. It's a way the numbers are coming from algebra of expectations, but that's an easy way to remember how it works. Is that cool? Is that better? Right? So
Yes, if the correlation between factors are zero, the indicator will be uncorrelated.
that's right. So that's what this implies. If you look at that correlation between y1 and y6, it should be lambda 1, 1 times the covariance of f1, f2 times lambda 6, 2. If this thing's 0, there should be no covariance, meaning no correlation between those two items. Right?
Which is what you want.
No, it's just a feature of it. I wouldn't say it's what you want, but if you think about what that does for a pattern, we're going to draw a correlation matrix, right, with 1s down at 3, 4, 5, 6. What you'd see here is two blocks. Imagine the factors were uncorrelated, right? You'd have a block with positive correlations over here. You'd have a block with positive correlations over here. Right? And then all the way up here should be, and all the way down here should be 0. Right? And so that's when you're saying, when you say, okay, here's my correlation matrix, I'm going to go see if the two-factor model fits it. It's looking to do this. Now, the higher the covariance between the higher the covariance or correlation, the bigger this it becomes non-zero and becomes closer and closer to the numbers over here.
But just to clarify, theoretically speaking, the matrix will be zero, like in the way that you specified before. But in reality, there might be value close to zero.
Right. Yeah. But if
So you would consider it as zero.
right. Well, I will tell you that if your estimate is exactly at 0, right, then you can go back to your correlation matrix. It will be exactly at 0. Or what's more likely to happen is this estimate's like 0.1, and yeah, those off diagonal blocks won't be exactly 0. They'll be somewhere in the smallish range.
And in the output of the analysis would be like non-significant p-value
For the covariance. That's right. That's right. Mm-hmm. So is this starting to make a little bit more sense? Pardon me? Yeah, if you saw that matrix right there and you fit this model, you'd most likely find this estimate to be 0, or when the p-value for it would be non-significant, right? It'd be effectively 0. Now, I will tell you, in a lot of the stuff that we do in the social and educational sciences, that rarely happens, right? Because things that come out of the same head get correlated, right?
The reason that I asked you.
Yep. Yeah, it's rare that happens. It is, I probably can count it like 2 times I've seen it in data in my career. So, and that's usually something called executive functioning. Yeah.
So if you have two factors that are opposing,
Mhm.
like say like a measure that measures like basic needs, satisfaction, and frustration,
Oh yeah. Mm-hmm.
then you would expect your covariance of your factors to be
Negative.
negative.
Yeah, it's possible that's the case. I mean, yeah, absolutely. If they're different polar ends, if they're unrelated, but they're still related. Sorry, if they're
Right.
inversely
Yes.
related. Absolutely.
Yeah.
Mm-hmm. That's exactly.
And then if they're both measuring satisfaction, then it would be 1.
It should be, yeah. And actually, that's another part. If you come into your analysis and you say, I've got 2 factors, but there's only 1, what you tend to see is this thing has a correlation of 1 because you don't see this pattern in your data at all. In fact, it's all very homogeneous.
Right.
So that's exactly it. But you can see now the philosophy of why we're confirming, right? We can say, I think there's 2. It should effectively, the best way of saying it, the strongest argument is this block diagonal, but it's usually somewhere in between. All right, I've got 1:15 on my watch. I need to stop. If you have questions afterwards, please let me know. If someone needs the room right afterwards, may have to step to the hall, but I will be able to answer each of your questions. Thanks. I hope this is starting to make a little bit more sense. I will also say that we're going to be doing this for still a number of weeks, but if you were to ask about what to read, take a look at that example. Just read it and try it, play it with the data and read the text, because that will tell you a lot of what we're going to talk about in class. And then if you want to supplement that, the chapters from the Brown book that we have, it's about CFA, they're really good too. All right. Thanks, everybody. Have a great weekend.